So hello everyone, welcome back. Now let us start problem number 230, which is on page number, problem number 8, 5.8, which is on page number 230 of Griffiths electrodynamics second edition. So it says that find the magnetic field at the center of square loop which carries a steady current I, and R is the distance from the center to the side, and the figure is given. So we have a square loop here. Alright, it carries current I, steady current, and we need to calculate magnetic field at the center of the square loop. So as we know that to calculate magnetic field at the center of the square loop, we'll just we'll take first of all one side, and we know that the angle between two sides is 90, and if we bisect them then it will be 45 degree. This is also 45 degree, and now we can apply a simple formula. I'll tell you the formula. Suppose if we are given a finite wire, suppose this is a finite wire, we'll consider one finite wire. All right, suppose this is a finite wire carrying current I, and we need to find magnetic field here. So what we'll do is, first of all, this is angle 45 degree, this is also 45 degree, and we'll apply the formula mu naught I upon 4 pi. The distance from side to center is given as r is the distance from side to center. So this is the distance r. It is given in the question, and the formula is sine theta 1 plus sine theta 2. Remember, this formula only applies when we take both the ends from the two ends of the wire. Suppose if the wire is somewhat like this, and like this, then this here comes a negative sign over here. If the we don't have these points on the ends of the wire, and this is given in one of the example of the Griffiths book also, but here the case is different. We have that both the ends, we have the connecting over both the ends, so we'll be using this formula, and we can clearly see that theta 1 and theta 2 are 45 degree. So mu naught I upon 4 pi r. So what is theta 1? Theta 1 is 45 degrees, so it is 1 by root 2 plus 1 by root 2, and it becomes as mu naught I upon 4 pi r into 2 by root 2. It means root 2, and it is just for one wire only. We have taken one wire na, so we'll multiply it by 4 because there are total 4 wires, 1 2 3 4. So net magnetic field at the center is mu naught I upon pi r into root 2. So this is the answer. Now coming to part number B, it says that find the field at the center of the regular polygon, n-sided polygon, we carrying a current I. Now he's saying that suppose we have a n-sided polygon, somewhat like this, and all right, we have n-sided polygon, and we need to calculate the magnetic field at the center. So we'll apply the same formula, mu naught I 4 pi r is the same distance, but here we can see that how is theta, how we are taking theta. Theta is total angle is suppose total angle is pi, and we are dividing it by the number of sides. You can see now a total angle here is 180 degree, sorry, pi means 180 degree, and the total number of sides are 4, so it means 45 degree. That's why we are taking 45. So we can generalize it for a polygon, that if a polygon has n sides, and we are taking it is common for all polygons that pi will be here, so theta will become as this. So both the theta will be pi by n, so it becomes 2 sine into pi by n. So simply we can just write this formula as like this: B at center, it is given by mu naught I upon 2 pi r sine n pi, or sine pi by n. So this is the magnetic field at center of a regular sided polygon. Sometimes the question can be twisted. He can change r. Suppose r is somewhat d cos theta. Cos theta means pi by n. Then our answer will change accordingly. This question appeared in one of the net exams of CSIR net. I hope you know that, which happens in India. So it is 2 pi, and we can say tan pi by n. This is a common formula that we see in our previous year problems of CSI or NET examination that is required for eligibility for a professor or so. So this is the answer for magnetic field at the center for a regular n-sided polygon. Uh, Sorry, regular polygon was given, na? So this is this. The figure should be symmetric, somewhat more symmetric. So you can imagine a regular n-sided polygon. We can draw like this also. Like this also. All right. Now coming to part number C. It says check your formula reduces to the field at the center of a square loop in a limit n tends to infinity. So he's saying that if the polygon is n-sided and we take n to be infinity, then it should be a circle. All right. N for a circle is infinity. Na? It reduces to the for a circular loop. So as n tends to infinity, how pi by n forms 1 by n or pi by n, it should go to 0 or it should be very small, very small. So or you can say that theta is very small, so sine theta should be theta, for theta very small. All right, we very well know that for sine for very small theta, sine theta goes to theta. So we can easily say that just a second. So we can easily say that magnetic field at the center can be written as mu naught I upon 2 pi r into sine theta 2 theta. All right, and theta or there was mu naught I upon 2 pi r into 2 pi, and they both got cancelled. We get mu naught I upon r, and this is for only half because we have taken theta as pi na. So this is only for the half portion, for this portion, and for the whole portion we can divide it by 2. So this is the magnetic magnetic field at the center of a circular loop. So that's all for this video. See you in next video. Bye bye. Thank you.